Turn on the tape. Okay, so we have this homework due tonight on surfaces in space. So that's very short. And again, maybe this table is helpful on that homework. Um, or I think in that homework you have a link to Wolfram. So you might be able just to, isn't there a link to Wolfram here? Let's see. There it is. Yeah. So you might be able just to type in the equation and say something like plot or graph. So plot or graph, and then type in that equation. Of course, you have to type that in on a single line in Wolfram Alpha. To get the exponents, you just use the caret key, right? The shift of the 6 key. Um, and just the slash, of course, will give you the division. And so Wolfram may also make a decent enough graph that you can identify, from this multiple choice, right? Uh, what the correct graph is. Some of these are not quadratic surfaces, though. This is a quadratic surface, but some of them are what are known as cylinders, right? And those are equations where you're missing, right, where you're missing one of the variables. Okay, like here we're missing x, so that means that this surface is um, since it's missing x, that means that it's going to extend along the x-axis. So you just need to think of what this curve looks like, okay, in the YZ plane, okay, what this curve looks like, and then you're just going to copy that curve, um, repeat that curve right along the x-axis. So probably something like this is the right answer. Is that it? Because I have a feeling that if you graph y squared plus z equals 7, that's going to be a parabola. And I think it's a parabola that opens down like this one, right? Okay. And so since the x variable is the one that's missing, you're just going to get copies of this parabola, right? Sort of duplicated there along the x-axis. So probably B there um, is the right choice. I'm just thinking there from looking at it. And then next time we have a little bit more complicated homework, only because I think it's got more computations involved in it, more arithmetic computations involved in it. But because it's dealing with functions, it may be a little bit more familiar to you than just abstract surfaces, right? Or arbitrary surfaces in three-dimensional space. So maybe you'll find this homework a little bit more comforting because maybe it seems more familiar since you're evaluating functions, which of course you've done a lot in your prior algebra classes. But remember, these are functions of several variables, right? Well, in particular, for the most part, I think functions of two variables, which is what we're dealing with in the class, right? So we're going to usually think of x and y as being the input variables to the functions. Since we have a pair of input values to the function, right, we usually think of the input to the function as being a point on the xy plane. And then the output value we usually think of as z, a number, of course, along the z-axis, right? And so when we plot our graph functions of two variables, we get a surface that's, either above or below, right? Or maybe going from below to above or vice versa, the xy plane, okay? So I think in this homework, you're asked to evaluate, functions of multiple variables, right, for particular inputs, and maybe ask some questions about the graphs of these functions, which again are going to be surfaces above or below the xy plane. Today, now, finally, notice we've got some terminology here that suggests calculus, right? Continuity, that's a calculus term. And certainly a calculus term is derivatives, right? Okay. So you can see we're finally here getting to the more familiar calculus parts of calculus 3. So last time we just briefly introduced the main questions that we're interested in. at least initially here, for functions of two variables. And they're the same sorts of, I mean, the sorts of calculus questions we're interested in for functions of two variables. And they're the same sorts of calculus questions we ask for functions of one variable that you're familiar with from calculus 1. So I'll repeat those in just a moment. And then we're going to use derivatives in this class, just like we use derivatives in calculus 1, to help us answer these fundamental calculus questions, right? That we're going to ask about functions of two variables. So that's kind of where we are. There's a broad overview of where we're at here. In the class for the time being. You will, this homework is because it deals with limits and continuity. This is going to be kind of abstract. But then when we start doing partial derivatives, this is going to seem very familiar to you. So I think you'll find this really straightforward, okay? At least doing the problems will be, maybe conceptually it's a little bit more challenging than it is in calculus 1, but actually I think getting the answers to the problems, I think, will be seeing kind of straightforward to you for the most part. Okay. So do y'all have questions before I switch here to the notes? Still missing Van. She should be here today. But anything y'all want to ask about before I switch to the notes? Okay, so again, this first notes on limits, you know, which are kind of sometimes tedious in calculus 1. They're going to be sometimes a little bit tedious here too, but we're not going to spend nearly as much time on limits as you do in calculus 1. And so it won't be that bad. And then, you know, continuity is kind of conceptually easy concept, but it's but when you put it in a rigorous setting, okay, when you try to give a rigorous explanation of continuity, then it becomes a lot more abstract concept, okay, and so you might find this a little bit vague, okay, but try to hang on, because then when we get to derivatives, this will be a lot more, as I said, familiar and feel a lot more concrete. All right, so let's go back to the notes that we started last time. And I don't think I posted these because we really didn't write anything into the notes, but we started talking about the notes, right? Okay, so so we're dealing here with differential calculus, right? Derivatives of functions of two variables. All the things that we say here, though, we could extend to functions of 3 variables or 4 variables or multiple variables, okay? But you won't get really to study those until unless you take a multi-variable calculus course, okay? So we're sticking pretty closely to functions of 2 variables, right? So we usually think of the 2 input variables as being x and y. And so an input to a function of 2 variables, we normally picture that geometrically as a point on the xy plane, okay? And then our output there from the function, right, the value we get after we plug our inputs right into the function rule, that value, we usually associate that with z, right, okay, and plot that along the z-axis in 3 dimensions. And so when you do that, of course, that's how you get the graph of the function, right, the geometric picture of the function. And we do want to, whenever we can, we do want to rely on our graphs of these 2-dimensional functions, I'm sorry, of these 3-dimensional functions, functions of 2 variables. But, you know, we're graphing surfaces, right? Okay, because these graphs are going to be surfaces, and not easy to graph surfaces, okay? So we won't be able to, unfortunately, we won't be able to rely on graphs to help us understand problems as much as we did in calculus 1, because we just cannot construct the graphs that easily, okay? But whenever we do get the chance, we'll try to look at the graphs, okay? Of course, it's a lot better now than, you know, when I was taking calculus 3, because you really couldn't make the graphs at all. All right, you just had to rely on what graphs had already been constructed in a textbook, right? Okay, you couldn't on the fly very easily at all do any graphing. And of course, there are advantages to that because you didn't have to think about it. So in some ways, you learn it better mentally, but then there are disadvantages too, right? Okay, so all right. So again, what are the key questions we're asking about functions of two variables in differential calculus? Integral calculus, of course, will be something different, but in differential calculus, well, one thing we want to ask is a function continuous, right? Okay. So over a portion of the domain, right, is the function continuous, meaning that informally, does it not have any holes or breaks or graphs in the surface, right? Okay, that's informally what continuity means. And actually, that informal definition is really all you really need, okay? But we're going to talk about the formal definition of continuity today also, okay? Because that's important because we're in a math class, right? So when we ask if a function is continuous, right, we mean, is it continuous for some set of inputs? And remember, our inputs we think of as points on the XY plane, right? Okay. So so when we discuss the continuity of a function, we'll be saying, is this function continuous over some region, right, in the XY plane? Okay. It won't just be a interval in the XY plane like it is in I'm sorry, it won't just be an interval on the x-axis, which is how you ask about calculus 1. Instead, we'll be asking about continuity over a region, right, in the xy plane, because the set of inputs for two variable functions is going to be in a set of points in the xy plane. It's going to be the xy plane. So here's an easy picture, right, of some function. I don't know what the maybe I do. I think it shows up later on in these notes, but we don't know it yet. So here's a two variable function, right? See, it's just a surface, right? So this function of two variables is not continuous at 0, 0, right? Okay, at the origin in the xy plane, because you can see there's going to be a hole there in the graph right there at the origin. Okay, so that causes you to have a discontinuity in your surface, correct? You have a hole in your surface, and so this function not continuous at the point 0, 0, the origin in the xy plane. Now, I don't see any other holes in this particular surface, though, right? Do you? At least they're not illustrated here very well. So it looks like maybe for the rest of the domain of this function in the xy plane, maybe this function is continuous, okay? On the other hand, if you patch up that hole, right, and again, I don't know what the formula for these two variable functions are, but if somehow you alter your formula so that hole gets patched up, right, okay, then you would have a continuous function, right? See, it's nice, and the surface there has no breaks or holes or what else could we say there? Gaps, right, in the surface. So it looks like this. It looks like this two variable function would be continuous over at least this portion. This portion of the xy plane. What portion of the xy plane is that? That corresponds to this circle, right, with radius 3, right, in the xy plane. Okay. Maybe the domain expands further in the xy plane, but at least this portion, right, of the xy plane is part of the domain of this function. One thing that sometimes confuses students about the concept of continuity is the surface does not have to be smooth. Okay, the surface does not have to be smooth. So you can have a very jagged surface. All right, these surfaces are very smooth. Okay, but you don't have to have a smooth surface. All right, for the function to be continuous, it just cannot have any breaks in it or holes in it, gaps in it. All right, but it can be very rugged. All right, so it can have all sorts of lumps in it or peaks and valleys in it, okay, and still be continuous. Now, again, obviously, this description of continuity is not mathematically rigorous, right? What do I mean by, the surface doesn't have any holes and breaks in it? Those are informal terms, right? Those are not mathematical terms. So we are going to come back and give a more rigorous definition of what continuity means, okay? And you did the same thing in Calculus 1 class, and you probably promptly forgot it, the mathematical definition, right? Because we always rely on kind of the informal definition or informal understanding of continuity. Right, now, the other questions that we want to ask, right, about these surfaces in these two variable functions in two dimensions, we want to know, is the surface rising or falling, right? Okay, so at a particular point, right, at a particular point on the surface, is the curve, is the surface rising or falling? And that becomes a more complicated question in 3 dimensions than it is in 2 dimensions. And we can illustrate that by picking a point on this surface, for instance, maybe right there. Okay, let's see if I can color that one. I don't want to pick the point at the top because that's kind of a special point, right? Okay, so let's not pick the point at the top, but let's pick a point right here on the on that kind of cone there, right? Okay, on that surface. So if I ask you, well, if you're going in this direction, right? If you're going in this direction, is the surface rising or falling? And you would say, obviously, what? Yeah, it's obviously rising, right? Okay, and so if you're thinking about moving along this vector, right? Okay, that's pointing like I've drawn here from this this point. Well, you would say, oh yeah, that surface is rising. Okay, and of course, if you look at the parallel vector, going in the opposite direction, right? Then of course it's falling, right? If you're moving that way, all right. But what's complicated though is that in 3 dimensions, right? So this doesn't happen in 2 dimensions, right? If you're on a curve in 2 dimensions, right, and you're thinking about moving away from that point, you're either going left or right from the right. So you're either falling or rising. Okay, but in 3 dimensions, you can move away from that point in multiple directions, right? So what if we went in this direction away from that point? Okay, we say that the surface is rising or falling in that case. What would you say, Elijah? Neither, right? Yeah, okay. Because if you're moving in this direction, right, you're sort of moving around that little circle there, right? Okay, and that means you're staying at a steady z value. You're staying at a steady z value. So you're neither rising or falling, right? Okay, so it's neither, right? It's constant. It's neither increasing nor decreasing, right? So so see, that illustrates the issue that comes up in 3 dimensions. In 3 dimensions, if you're talking about whether a surface is rising or falling, since you can move away from a particular point in multiple directions, okay, you might get multiple answers to this question depending on which direction you're moving away from the point, okay? So that does not happen in Calculus 1, right? If you're at a particular point on a curve in Calculus 1, the curve, you either have to go left or right, okay? And there's really only one answer to the question if the curve is rising or falling at that particular point. Okay? But in 3-dimensional calculus, right? Okay, since you can move in multiple directions away from a point, you might get different answers to whether the surface is rising or falling. Okay, at a particular point. All right, so that makes things complicated in 3 dimensions. But nevertheless, okay, that's the question that we want to take up, right? On a surface at a particular point, is the surface going up? Is the surface going down, right? Okay, how is the surface changing at that particular point? And then the third thing, of course, is what is the curvature of the surface at the point? Okay, so is the surface kind of forming a hill at a particular point, right? Okay, or is the surface kind of have a cup shape at a particular point, right? In calculus 1, we refer to that concept as the concavity of the curve, right? Okay, and also in calculus 2, we're going to refer to in calculus 3, we're also going to refer to that as the concavity of the surface at a particular point. Okay, but again, as we illustrated last time, because you can move multiple directions away from a point, right, on a surface, you might get different answers to what's the concavity of a surface at a particular point, depending on which direction you're thinking of moving away from that point. Okay, and I think we showed a picture of that last time, but I don't know what I did with that curve, so I'm not going to be able to illustrate that again for you. Okay, yeah, Fatin. Yeah, and does not exist is a possibility too, right? Because if you're on a plane, right? Okay, a plane is a surface, right? Okay, so if you're on a plane at a particular point, there is no concavity, right? Okay, because the surface is flat, so you don't have any curvature, right? Okay, I guess that's not the same as does not exist. There you would say the concavity is 0, right? You just don't have any curvature, right? But we can have doesn't exist. Okay, that would happen. That would happen, I think, on a surface that looks like a cone like this. Okay, I think at this point, right there at the top, we can't talk about the concavity of the of that surface at that sharp point right there at the top. Okay, of that cone. Okay, now we're going to use to answer these questions, except for continuity, we're going to use for direction and for curvature, we're going to use the process of differentiation. We're going to use derivatives, okay, adapted to two variable functions to answer these questions, just like we do in calculus 1. Right? So nothing here is going to seem too mysterious, okay, except we do the differentiation in a slightly a different way, all right, okay? And again, as I mentioned, we have to be more careful about discussing, well, what direction are we moving away from the point, right, okay? What direction do you want to know? Is it increasing or decreasing? A question that you don't have to worry about in calculus 1. Now, for continuity, however, we don't use derivatives to answer questions about continuity. Instead, we use the notion of limit. And so now I need to introduce the idea of limits in 3-dimensional space, right? Or for functions of 2 variables, okay? Forgot what else I was going to say here, but I forgot. All right. So here now is the formal definition of continuity. All right, it has 3 parts to it. This is really analogous to the definition of continuity that the formal definition of continuity that you learned in calculus 1, but you have probably forgotten about this definition of continuity from calculus 1, okay? Because you don't spend a lot of time on it, all right? And some students never really understand it very well, even in calculus 1. Right. So, formally here, right, we say a function of 2 variables, right? Okay, x and y. There's our output variable z, is continuous at some point. So this is a specific point. All right, in some region of the domain for that function. Okay, if the following is case. So remember, domain is a is a set of inputs in the XY plane, right? Okay. So so when you draw a region in the XY plane, right, you get well, a region, right? Okay. So here's what has to be true for the two variable function to be continuous at a particular point, right? First, the function has to be defined at that point. Okay. Remember, this is a specific point, right? Okay, this is the function, but this is a specific point on the XY plane. The function has to be defined at that point. So if the function doesn't exist at that point, then obviously you're going to have a gap in the graph at that point, right? If the function does not exist at that point, then you've got to have a gap in the graph. So that means the function is not continuous at that point. So that's the easy thing to check first, by the way, if you're asked about is a function continuous at a particular point. Make sure that the function is defined at that point. Make sure that that point is in the domain of the function. Because if it's not, then the graph has to have a gap in it at that point. So you know it can't be continuous there, right? And that's frequently, by the way, this first condition is frequently what keeps functions from being continuous at particular inputs, right? Okay, so that's why I say check this first. All right, so that's easy thing to check. Now, the other two things are what's harder to check, okay? So what this second thing says, and I'm going to illustrate this for you, but it says that if the limit, okay, if you take inputs that are approaching your given input, that limit has to exist, okay? So if you have inputs that are approaching your a given input, this is where you're trying to see if the function is continuous, right? Okay, then that limit has to exist. Now, what do I mean? What do we mean by these inputs of two variables approaching a particular input, right? Okay, look at this picture. All right, so here we imagine this as being our point x sub 0, y sub 0, right? Okay, and then just let's just pick some other arbitrary point out here. Okay, so what this line 2 means is if you, did I close that? If you let inputs approach the input in question, so if you let them move to the input in question, right? Okay, if you let them get closer and closer to this input in question, then this limit of the function values has to exist. Now, what's a little bit tricky though about this line 2 is we're in two dimensions here, right? Because here we are in the XY plane. So how can you let your inputs approach this point x sub 0, y sub 0? I drew one picture here of an approach, but notice you could have let the approach come from lots of different directions. We could have thought of the approach as coming like this, you see, okay? Or we could have thought of approaching this point like this, you see? And from all of those different directions, that limit has to exist, okay? So in other words, if you're computing for points along these paths, right? If you're plugging those points into your function and computing the output values, right? Okay, those output values have to start converging to a limit, right? Those output values have to start converging to a limit. Furthermore, here's the last key part. That limit has to exist, and it has to be the same as the function value at your given input x0, y0, okay? So this limit has to exist, and it has to be the same as what you would get if you plugged in x0, y0 into your function. Let's look at another picture of this. But let's move it to 3 dimensions. So again, you can maybe understand this a little bit better. Let me see where I put my picture. Oh, right here. So I don't know. I have no idea what this surface is. This looks like some kind of, what does that look like? What's that thing called? Huh? Like what? This, a ghost? Yeah, all right. A little bit more formally than that, though, Robert. Okay. That looks like some sort of quadratic surface. Which one? Is that that's the very first one, isn't it? Or is it? Oh, maybe it's an elliptic parabola. Okay. Yeah, maybe an elliptic parabola. Part of an elliptic parabola. Okay. So maybe that's what we've graphed here, right? So remember, okay, our inputs are points in the XY plane, right? Okay, our inputs are points in the XY plane, right? And then, of course, you plug those inputs into some formula, but I don't know what the formula for this surface is, right? And you get output values, right? And if you plot those output values for this particular function, you'll get this nice surface. Right now, what we want to know is the surface continuous? Is this function whatever this function is it continuous at this point, x sub 0, y sub 0? And I just happen to position that point right there. Okay, so where's the output from this function for that point, x sub 0, y sub 0? Well, of course, you just go up, right? You go up vertically from the xy plane until you hit the surface. So there's the output, right? Right there. Okay. Right there on that surface is the output. So that's f of, you'll see that very clearly. Yeah, better, a little bit better on the screen than I can see it. That's f of x sub 0, y sub 0 is right here. Okay. And I want to know, is it continuous? Is this function continuous at that point? Well, does it look like it's continuous at that point? Do you see any breaks there in the surface at that point? No, I don't. Okay. So yeah, I think it's continuous right there. Okay. I mean, visually, it certainly looks continuous, right? It doesn't look like there's any hole there in the surface at that point, right? Okay. That point's definitely in the domain because that f of x0, y0, right, is part of that surface, correct? So it looks like it's continuous, but that's very informal, right? To say, oh, it looks like it's continuous, right? The mathematical test is more rigorous. All right. So the mathematical test says, okay, here's what we're going to do. We're going to pick points out of the XY plane, right? And we're going to let them approach. We're going to let them approach our given point x0, y0. Okay. All right. So here's one approach that I took. So here is this kind of constant approach right here. So what do these points xy look like in the xy plane? Notice what in these points, what's changing? I'm talking about points along this line. What's changing there for these coordinates? The y coordinate is changing, right? But the x coordinate is fixed, right? Okay. It looks like it's about 1/2 because this is one on the x-axis. So it looks like we've fixed the x value here at 1/2, and then we're just letting the y value get smaller and smaller, right? Until the y value is approaching whatever the y sub 0 is here, which looks like also about minus 1/2, correct? If you look on the y-axis, it looks like y sub 0 is probably around minus 1/2, but I'm just guessing at that, right? Okay, so let these points on your xy plane approach your given point x sub 0, y sub 0. Now, compute the outputs from these points. So if you compute the outputs from all of these points, right, approaching x sub 0, y sub 0 along this line, what are those outputs going to look like? Well, you can trace them out on the surface, right? Aren't they going to look like this? Okay, they're going to be above this line right on the surface, correct? Right. So I think those outputs are these points on the surface. or those values on the surface, right? So for the function to be continuous, right, what do we want to be the case? As these points are approaching the point x sub 0, y sub 0, what do we want the output values to be approaching? Also, the output from x sub 0, y sub 0. Is that happening here in this picture? Does that look like what's happening? Yeah, right. Okay. As these points are approaching x sub 0, y sub 0, aren't these points on the surface also approaching f of x sub 0, y sub 0? Yeah. Okay. I think that's true. Now, we would need the formula for the function f, right, to test this analytically, okay? But it certainly appears to be the case on the graph, right? So I think it's true, at least from this direction, right? Okay, it looks like the limit of f of xy as xy approaches x sub 0, y sub 0, that limit is going to be f of x sub 0, y sub 0. All right, how do you write that down? How do you write that down in calculus terms, right? What I just said in words, right? Remember, it's the limit as your points approach your given point, correct? You want the limit of these output values, you want them to turn out to be f of x sub 0, y sub 0, right? Okay. So you want these values to turn out to be approaching this value. That certainly appears to be the case there on that surface. But of course, we're in 3 dimensions. So what's the icky complication here? I just chose what? I just chose one direction to approach this point. But in how many directions can we approach this point? Infinitely many, right? Okay. So technically, I have to test every single possible direction. All right. Of course, I'm not going to be able to do that in the picture, right? But mentally, I'm going to be much more adept at doing that. All right. Believe it or not. Okay. Here's another direction, though. I just drew one other direction just for fun here. All right. So let's look at coming in from this direction. Let's look at coming in from this direction. So that looks like I'm coming in on what line? What line does that look like? It doesn't even look like that line. Okay. I was thinking maybe that was the 45-degree line. Okay. In the XY plane, the equation for that would be x equals y. All right. So maybe I was thinking of these two coordinates as being the same. Okay. X equals y. All right. And approaching this point. Well, anyway, even if this is not a 45-degree line perfectly, we're thinking of approaching along this line, right? Okay, from this direction. Now, if you plot the outputs from points along this line, notice you get a more interesting curve here, right? Okay, because notice that these points are going to go over the hill here, right? So they're going to go up, and then they're going to start coming back down again, right? Okay, so you see that I just think of putting these points along this line into my function formula and seeing where I ended up on the surface. Well, you end up on the surface, along this curve, right? So as xy is approaching along this line, as xy is approaching x sub 0, y sub 0 on the surface, you end up going up, right, and then coming back down. But nevertheless, even though you go up and come back down, eventually what happens? Do your output values on the surface start approaching f of x sub 0, y sub 0? They do, right? Okay, at least in this picture, they do start approaching. So yeah, I think this is still true. Okay, I think this equation, this limit is still correct, even from this direction. But remember, we have to be able to imagine going from any direction, right? Okay, to this point. Will the output values eventually converge to f of x sub 0, y sub 0? Well, I think in this picture, you can convince yourself, yeah, if I approach from any direction, the way this surface is shaped, right, my limit will always end up being f of x sub 0, y sub 0. So I definitely think that the surface is continuous at I definitely think the surface is continuous at this point. In fact, I think this surface looks to be continuous everywhere, right? Okay, in this picture, the surface appears to be continuous. All right. Well, so there's kind of a visual illustration of what we mean by limits and continuity. Let's see if we can let's see if we can test that out analytically, though, without a graph. So I want y'all to tell me what y'all think here, okay? All right, so we're interested in knowing just this limit. I'm not really testing. I'm not really testing continuity here of this function of two variables. I'm just seeing if I can convince myself that if I can calculate this limit. All right. So we were thinking, so what happens if we have points in the XY plane and they're approaching this point 1, 2 in the XY plane? Okay. Then what's going to be happening to these output values from this expression, from this function of two variables, right, as our input values, as our input points approach the point 1, 2. Well, look, in calculus 1, how do you often evaluate limits? You don't have to think about it too much. What would you just do to evaluate the limit here in the calculus 1 class? Plug it in, right? You would just plug in the limit point right into the formula, and you would assume that that's probably going to be the right answer, correct? Okay, and unless something else goes wrong, right? Okay, you would assume this is the correct answer. Robert, the reason you can make that assumption is it's because often this function will be continuous. Okay, so if that function is continuous at this input, then that assumption is correct. Okay, you can just evaluate the limit by plugging in the limit point. All right. Well, let's just try it here and see what we get. So let's see. I'm going to plug 1 in for x, right, and 2 in for y, and so we get this. And so what's that? 20 over 5. Is that right? Which is 4. So I would think there, I'm guessing here that that limit is really okay. I do have a picture of this though. I think. Oh man, okay. It's not a very good picture though. I think this is the graph of that function, 5x squared y over x squared plus y squared. So can we find the point 1, 2? Oh, I think I already plotted it there. There it is. There it is right there. Okay. I didn't plot enough of the surface to see the surface around both sides of this point. Okay. But there's the point on there's the point f of 1, 2 on this surface. So that is that. No, that doesn't look right, does it? Is that the same formula? Oh, that's not the same formula, is it? Oh, shoot. Okay. Oh, I thought I had it graphed. Let me see if I have it graphed somewhere else. Maybe I don't. I wasn't looking carefully enough. No, that's not it. Okay. Well, never mind. I don't have an illustration of that. Okay. So I thought I had a nice illustration of that. No. All right. Okay. So if we can assume that 5x squared y squared over x squared plus y squared, if we can assume that formula is continuous at the point 1, 2, then we know that we can evaluate this limit just by plugging in 1, 2 into the formula. Why is that the case? I said if we can assume this formula or this function is continuous at this point, then we know we can evaluate this limit just by plugging the 1, 2 into the formula. That's because, right, if a function is continuous, right, then you know from the fact that it's continuous that this limit has to be the same as evaluating the function at that particular image. All right. So this is going to be true if f of xy equal this formula is continuous. Now, I really don't know, of course, that that's continuous. So maybe I'm making a false assumption in assuming that that this equation is true, right? Because maybe this function is not continuous at this point. However, this function, so I'm going to give you a little secret here. This function is what's known as a rational function. That's the quotient, the ratio of two polynomials. The numerator here is a polynomial because we only have whole number powers. I'm sorry, non-negative whole number powers of variables. Okay, this is x to the first power, and this is y to the second power. And same thing so that makes the top a polynomial, and the bottom is also a polynomial because again, you only have a positive, non-negative whole number powers of your variables. Okay, this is 2, this is 2. Those are non-negative whole numbers, right? So if the top and the bottom of this fraction are both polynomials, then you know that that's a rational function, and rational functions are continuous. Okay, so we know that from theory that rational functions are continuous everywhere in their domain, so be careful about the domain. Polynomials are also continuous, okay, everywhere in their domain. Okay, so if you have a polynomial function, you automatically know it's going to be continuous. Did you have a question, Elijah, or you just
so
Mhm. Yeah, so that's but you're wondering, well, does that limit exist? Okay. Well, yeah, there's something special about 0 divided by 0. Okay, that's often an issue with limits. That's called an indeterminate form, and that's going to come up here in a moment. But notice that you don't have to. The idea of continuity doesn't apply at the point 0, 0 because that's not in the domain, right? Yeah. Okay. So we couldn't say, well, the limit has to exist because the function is continuous at 0, 0. No, it's not continuous at 0, 0 because it doesn't exist at 0, 0. Right? 0, 0 is not. Okay. All right. So this one, you can evaluate this limit easy just by plugging in the values. Okay. And that frequently works. Okay. Because we frequently will be dealing with continuous functions. All right. Okay. Let's try this one. This one also is continuous everywhere in its domain. Okay. All right. Because that also is a rational function. The top is a polynomial. Constants count as polynomials. Why is 1, the constant 1, a polynomial? Because that's 1 times x to the 0th power, or you can also think of it as y to the 0th power in this case, or x to the 0th power times y to the 0th power if you wanted to. Okay, but 0 is a non-negative whole number. Okay, so you only have non-negative whole number powers of your variable, right? Same thing in the bottom. You just have 2 x squared, y squared. So your exponents in your bottom are non-negative whole numbers. So this is a polynomial divided by a polynomial, so it's a rational function. So it's going to be continuous everywhere in its domain. Unfortunately, as Elijah was asking me a moment ago, 0, 0 is not in the domain. Okay, oops. So you cannot evaluate this limit just by plugging in 0, 0. And if you do try plugging in 0, 0, of course, what happens there? You get 1 over 0 squared plus 0 squared, and that is undefined, right? So, darn. So I wonder about this limit. Well, this is one you can just think about, all right? Um, uh, 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 you don't need a graph would be helpful, but a graph would be helpful here, but uh, I don't think you need the graph because if is xy is approaching 0, 0, no matter what direction you're coming from, positive or negative, right? As xy as your input point is approaching 0, 0, both xy and are getting very small, right? They're going to be ultimately getting very, very tiny, very, very close to 0. So if you take those very small numbers and even if you square them, you will still have a very small number, right? And if you divide 1 by a very small number, what's happening to that quotient? What happens when you divide 1 by very, very tiny numbers? What happens to that quotient? You get really, it gets really big, right? Yeah. So eventually this fraction is going to start getting really, really big, right? Okay. It's, by the way, it's always going to be positive because x squared plus y squared, since they're squared, they will be positive. So the denominator is positive, but it's still a small number when x and y get really, really tiny. So you're dividing positive 1 by a really tiny positive number. That's going to get really, really big. Okay. So actually, the limit is, although formally the limit doesn't exist, you can write down a limit here. It's positive infinity. Okay. This fraction is blowing up to really, really big. Oh, this is the that formula is the first graph we saw. That is this picture. This is 1 over x squared plus y squared. Okay, and so you can see what's happening as x and y get close to 0, right? As x and y both get close to 0, what's happening to these output values? They're shooting up, right? Okay, they're going to get really, really big. They're going to get to positive infinity. So, so the limit doesn't exist. Well, except you could say it's positive infinity. All right, now this is so this is the one where I have here's the one where I have the graph. Okay, so let's see if we can figure this one out. This one's tough to figure out. Okay, so so this is this is not quite the same as example 1 there, okay? But this also is a rational function, okay? This also is a rational function because it's a polynomial. The top is a polynomial, so this is x squared y to the first power. Those are non-negative whole numbers, so that's fine. And say, of course, 2 and 2 are non-negative whole numbers, right? So you have a polynomial divided by a polynomial. So this is a rational function, and it should be continuous everywhere in its domain. Unfortunately, what's not in the domain here? Yeah, okay. So so we cannot evaluate this limit just by plugging in 0, 0. Too bad, all right? Almost any other limit for this function, we could evaluate it just by plugging in the limit point, right? Okay, into the formula. But not this one. Now, when you do try to plug in 0, 0, of course, what do you get? You get 0 divided by 0, all right? So in this example, this was slightly different. When we plugged in 0, 0, we got 1 divided by 0, okay? But this is 0 divided by 0, and 1 divided by 0, and 0 divided by 0 are different sorts of things, okay? Of course, this is still appears 0 divided by 0. You can't calculate it, right? So it's undefined. But when you end up with the limit that you think is 0 divided by 0, that is what's known as an indeterminate form. So that tells us that the limit may actually exist, okay? It may not, all right, but it might exist. And so you have to do a little bit more careful exploration of what's going on, right? To do the careful exploration here, we have tools from calculus that can help us with that, all right? But for the time being, we have analytical tools that can help us with that. But for the time being, we're just going to have to rely on the graph. So here we really are going to have to look at the picture and see if we can convince ourselves if this limit exists or not. All right, so here's the graph or part of the graph of this formula, 5x squared y over x squared plus y squared. So looks like this. And we're interested in the point 0, 0, right? So there's 0 on the y-axis, and here's 0 on the x, so it's right here. So as you're approaching that point, right, as you're approaching 0, 0 from different directions in the xy plane, hard to picture that, okay? So again, think of things out of the xy plane, and I'm let them get closer and closer to 0, 0 in the xy, right? Okay. So what's happening to my output? What's happening to this surface? What's happening on this surface as get closer and closer 0, 0 in the xy plane? It looks like the surface values are dropping off the what? Here. Like they're dropping off. They're not falling off the negative. Okay. Or not shooting off the positive. It looks like the surface is coming down here to okay. Yeah. We should look a little bit more carefully though, because notice this portion of the xy plane, that's all the first quadrant. So those are only positive x and y values. So let's look at other side surface. Okay, so let's graph a little bit bigger piece of that surface, and let's see what's happening on this side. Okay, now on this side, let's see, we've got that's the third quadrant, right? Because we've got negative x values and negative y values, right? Okay. So where's the origin? Right there. That's 0 on the y-axis and 0 on the x-axis. So again, think about what's happening as we trace points out in the xy plane, right, that are moving closer to x being 0, y being 0. What are happening to the output values from the function? What's happening to that circle? Appears to be climbing up to what? Back here, right? So on the z-axis is what? That's 0. So it looks like it's coming back up. Z equals 0. Oh, so yeah, that's not all sides of that surface, all right? I just looked at the first quadrant. Okay, there's also the second quadrant, the fourth. Can't see, but that may give us an idea that this limit does exist and is in fact what? 0. Okay. So this surface, as we get closer to 0, 0 on the xy point, which is right there, this surface is not shooting off to infinity, falling off the negative. It looks like it is merging right to 0, 0. So, so we're thinking, oh, that limit does exist. That limit does exist, and in fact, I think it's 0. Whoops, is that the one? No, wrong limit there. So I'm thinking this limit does exist and in fact is 0. But I'm not 100% certain of that, okay? I'm just thinking that looking at the, I'm just thinking of that looking at the graph. Okay, let's try one more. So here I have a tougher formula. This is a really terrible formula, right? X squared minus y squared over x squared plus y squared squared. Okay, and right, this whole thing is squared just to make it worse. That formula, that function is continuous. That is continuous. This is still a rational function, even though it's squared here. This is a polynomial divided by a polynomial, because these are a positive whole number powers of x and y, right? And even if you're squaring it, if you were to square out this expression, it would take you a minute or two, right, to expand this square. But even if you expanded the square, you'd still get a whole number of powers in the numerator, positive whole number of powers in the numerator, positive whole number of powers in the denominator. So you would still have a polynomial divided by a polynomial. We'd still have a rational function. So everywhere in its domain, this function is continuous in its domain. Okay, but unfortunately, the domain does not include 0, 0. Okay, so we cannot conclude that this limit is anything. All right, and what happens if you try to plug in 0 and 0 into this formula? Of course, what do you get again? Is that 0 divided by 0 again? Yeah, which again is this so-called indeterminate form. So maybe this limit exists, or maybe it doesn't. Maybe it does turn out to be positive infinity or negative infinity. I'm going to show you a graph now of this surface. This has a wild, you can imagine this is kind of a complicated formula. So you get a wild graph of the surface. It looks like this. So it's a very nice surface. Okay. So you've got these nice undulations there in the surface. Very pretty. Unfortunately, you cannot see exactly what is going on right there at 0, 0. All right. Can't see that. It doesn't look, however, like the surface is falling off to negative infinity, right? Because I don't see anything down here. And it doesn't look like the surface is shooting up to positive. Okay, right? Because I can't see anything, see any part of the surface right there. But I can't tell because it's obscured right by the surface. I can see what's happening. But there's a chance, I think there's a chance that there be a proper limit. Looks like it have. It doesn't appear to be shooting up positive. All right, but we're gonna get fooled, okay? Because unfortunately, I see behind the surface. Something funny is going. All right, let me show you what we're. So, all right, so you have to show this, but some part, but it does illustrate the complexities here that occur. So let's try approaching that point 0, 0. Let's try approaching along this path. So along the y-axis from this direction. Let's draw a picture of that. So right here, we're going to try approaching 0, 0 along this path. So what path is that? That's along a line in the XY plane, right? What line is that in the XY plane? That's x equal y, okay? That's x equal y. That's the 45-degree line. All right. So let's assume that we're going to calculate the limit by approaching the origin along this 45-degree line. So you just told me there, Robert, that along the 45-degree line, x is equal to y, right? So when we're computing this limit along that 45-degree line, what limit there are we really approaching? I mean, what limit are we really computing? What's really going there to 0, 0? What do all these points look like? XX, right. The x coordinate and the y coordinate are the same, right? So what do you get in this formula when the x coordinate and the y coordinate are the same? You get this, right? But that limit, I think we can figure out. What is that? That's 0 over 2x squared, and that limit is going to be what? 0, right? Now, you may object and say, but eventually, if x goes to 0, won't this denominator also go to 0? But remember, this is a limit, so your point is approaching this point, but it never has to touch that point, all right? You're just thinking, what happens as your point gets close to this point, but never touches it? I forgot to say that earlier, right? You remember that from Calculus 1, when you're computing a limit, your limiting value, your values get close to the limiting value, but they don't actually hit the limiting value, right? Same thing here. So x is actually never going to be 0. It'll always be non-zero, but the top is going to be 0. So all of these fractions will always be 0 squared, which is 0. So this limit does exist at 0. Oh, so the picture, kind of what we expected there, right? The picture is kind of clear, right? It looks, what did that look like? It looks like the surface along this line appears, this surface is always down there at 0, right? Along this line. It just stays at 0 along this line, right? So limit is 0. Makes sense. Now, I'm going to go in from another direction. Let's go in along x-axis. Right, so this direction on x-axis. Now, there the surface is more interesting, right? Look at what's happening above the x-axis. Here's the surface. So you're kind of on this peak, right? On this ridge, right, in the surface. But as you're getting close to the origin, it looks like this ridge is dipping, right? Suddenly falling off. All right, so let's try from that direction. And that direction, really can't see very well from that direction. We can't see what's happening. The surface is falling off there. Right? So walking along this ridge, suddenly come to, it's not quite a cliff, but it's pretty steep. Looks like it's falling off to, again, it looks like it's falling off to 0, but let's see what's really happening. So let's try computing that limit a second time. May not write you there. So what do these points look like as you are approaching along the x-axis? Y is always equal to 0, right? Y is always equal to 0. So you have x can be anything, right? Of course, x is getting small, but it's going to 0. But the y is fixed at 0 on those points. So in your formula, you can just plug in 0 for y, right? So what does all this reduce to? Is it just x squared over x squared squared? But what's that? It's 1. Yeah, okay. So the limit there is really 1, not 0. So What about this limit then? It doesn't exist, right? So why doesn't it exist? These two limits exist, but they don't agree, okay? Because this one is 0 and this is 1. It has to be the same limit along all paths approaching 0, 0, okay? And since they're not the same along all paths approaching 0, limit doesn't exist, all right? Okay. Let's think quickly now about continuity in a few examples. So I just want to I've got some nice surfaces graphed here, and I just want to see if we can figure out where these functions are going to be continuous or not. So this first one, x cubed plus 2xy minus y squared, that is a polynomial function. Because again, remember, only have non-negative whole number powers of x and y input variables. And they're just being added and subtracted from. So that constitutes a polynomial. Polynomials are the nicest sort of functions, right? They're continuous everywhere. Okay? So this one is continuous everywhere because it's a polynomial. There's a graph of part of that surface, right? Continuous everywhere because it's a polynomial. When I say everywhere, I mean all over the xy plane. Okay? It was entire xy plane, right? Okay, that surface is going to exist. Sometimes it may be below the xy plane. Here it's here it is below the xy plane. Sometimes it may be above, but it's there. But no holes are break. This is a rational function because the top is a polynomial and the bottom is a polynomial. So you're just taking the quotient of polynomials. So that is also continuous everywhere for its domain, but unfortunately the domain is not everything. What's missing from the domain? 0, 0. X and Y cannot be both 0 simultaneously, right? Because then you'll be dividing by 0 in your function. So not continuous at 0, 0, which is the origin right here. So if you make a graph, you can see the function on left and the right. So not continuous at 0, but everywhere else. Now, I think this next example also is a polynomial. Oh, yeah, it is a polynomial. Because you have a constant polynomial in the numerator, and that's a polynomial in the denominator. So again, it's going to be continuous everywhere except for things not in the domain. And of course, you're going to be missing things from the domain where the denominator is 0. So what you have to figure out is where is the denominator 0? So you'll take the denominator and set it equal to 0, and you end up with this curve, okay? Right? Solutions to this equation are going to be a curve. What sort of curve is that? That's parabola. That's just the standard parabola, y equals x squared. Okay, so this function in 3 dimensions continuous everywhere except along this parabola, because the values on this parabola are not in the domain of that function. So there is that parabola, y equal x squared, graphed in the xy plane. There it is, that dashed line. And so that surface doesn't exist above or below that dashed line. Okay, so your domain is everything except for this curve, y equals x squared. So you get a picture that looks like this, as it turns out. Okay, notice around that curve, the surface starts around this parabola, right? The surface starts falling off because or shooting up, because the graph doesn't exist above that. Graph doesn't exist above that parabola. So you could figure out that the graph doesn't exist, right, for this curve, right? But graphing this, of course, would be tough. Not going to be easy surface to, not going to be an easy surface to graph. Oh, there's all my examples. Wow, cool. All right. So that's really all we have to say about limits and continuity. All right. So I'm not going to be spending a lot of time talking about these things in 3 dimensions. All right, now we want to get on to the fun stuff, because now we want to start talking about derivatives. Okay, and this will be more interesting because it's going to seem more familiar to you. All right, let's take a few minutes. So let's break here until about 12:55. Okay, and then we'll come back and spend the last 20 minutes here talking about getting started with derivatives. Everyone who takes the class says, well, I didn't really like this stuff at the first. I didn't like it till I got to derivatives. So you'll see if we can get to at least one example of what we're going to do. So we're thinking about the question of is a surface rising or falling at a particular point, and how fast is it rising or falling? What's the rate of change of the surface at a particular point, right? Okay. So I often think of that as function direction. Okay. Is the surface going up? Is the surface going down? What's the direction of the surface at a particular point? And how fast is it going up? How fast is it going down, right? How can we measure that rate of increasing or decreasing, right, at a particular point? So we're gonna pull a classic technique from mathematics. All right. So do this all the time in math. All right. This is what research mathematicians who are discovering new mathematics do all the time. We're going to reduce this problem to a problem that we already understand. All right. So we're going to simplify the problem to a problem that we know how to do, and then try to work backwards from the simplified version of the problem. All right. So I've got so I'm dealing with a function in 3 dimensions, right? A function of 2 variables. So, right. So I want to reduce that to a function of 1 variable, because I know how to do 1 variable calculus. All right. And then once we've solved the problem in that simplified setting, we'll see if we can work backwards and think about the more general problem. All right. So the way we're going to reduce this from a function of 2 variables to a function of 1 variable. So the way we're going to move from calculus 3 back to calculus 1 here is, in my function formula, I'm going to think of holding one of the variables constant. All right, so I'm going to think of holding either x or y constant, right? Now, if you hold x or y constant, then that essentially eliminates 1 variable from the equation, because that variable becomes a number now, not a variable. And so you end up with an equation with 2 variables. And that's what we're used to dealing with in calculus 1, right? We have the input variable and the output variable, right? So that's what we're going to do here, right? We're going to turn the calculus 3 problem into a calculus 1 problem just by holding one of the variables constant. So let me show you let's take an example of this, all right? Because until you see an example, it won't make any sense. So let's go back to this polynomial surface. x cubed plus 2xy minus y squared. So we saw a picture of that a moment. All right. And what I want to do is find an equation for the curve the curve, not the surface, the curve that we get when we hold y equal -1. All right. Okay. So I'm going to think of setting y equal to -1, holding y constant at -1. There's no reason I chose -1. That was just an example. All right. So I could have picked any constant value for y. It could have been 0, +1, or anything. All right. Just in this example, I decided to let y be -1. So first, what formula do we get here, right? Okay. What function do we get when we set y equal -1? Well, now x is still a variable, right? So that's not going to be any different. But y, again, we're setting that to be -1, right? So I'm going to plug in -1 for y. So you get z equal x cubed. What is that? -2x -1. Is that right? Yeah. So you get this curve, z equal x cubed minus 2x minus 1. So notice that's a function of two variables, z and x. And so when you graph that, you're going to get a curve. Let me show you a picture of that curve. Let's scroll down a little bit here. So there's the actual surface. That's the entire function of two variables, right? But I'm thinking of, what do I get when I set y equal to -1? All right. So what do we get when we set y? There's the y-axis, right? So we set y to -1, right? So notice that you don't get an entire surface, right? Just get a curve, and here's the curve actually the curve actually. Its variables are z and x, right? X is changing, and of course z is going up or down, right? Okay, depending on the x value, right? But the y, of course, is fixed at -1. So you get this curve. By the way, that's the same as when you set y equal to a constant. What you're doing is you're essentially intersecting a plane, okay, with your surface, all right? So in this case, we would be taking the plane, y equals -1, which, by the way, is parallel to the xz plane. Taking that plane, so it's going to be this picture, it's upright plane, and you're intersecting that with the surface. In other words, taking the trace of when that plane intersects with this surface, and you get this curve that looks like this. That curve kind of makes sense because what is that formula? Let's look back at that formula. What kind of function, what kind of two variable function is that? Is this thing? It's a polynomial of degree what? 3, right? So that means it could have, we know from calculus, right? From calculus 1, that means it could have two turning points, right? One less than the degree. It may have a peak and a valley, one less than the degree. And I think that's exactly kind of what you see here, right? On this curve, right? I think we're going to have a peak somewhere over here. And I think if you went further out the surface in this direction, it looks like that curve is coming down to a valley, right? And I think it would probably, right? So it does kind of look like it does kind of look like a curve, right? Traced out on this traced out on the surface. Now what we can do, of course, is answer questions about this curve using one-dimensional calculus. But since this curve exists on the surface, we'll also be kind of answering questions about the surface as well. Okay. All right. So let's see what kind of questions we ask here. All right. So find the slope of this curve, when x is equal to, find the slope of this curve, right? When x is equal to -1/2. Well, of course, how do you do that? You take the derivative, right? So let's take the derivative of this formula. So that would be what? dz dx, right? And what's that equal to? 3x squared minus 2, right? And then you're going to evaluate that, of course. I should have put that in at the same time. You're going to evaluate that what when x is equal to minus 0.5. So if I use, the old-fashioned notation for derivatives, uh, here's evaluating this derivative at x equal minus 0.5. Let's see, what is that? So that's 3 times minus 0.5 squared and then minus 2, right? So that's going to be, let's see, I think that's 3 times minus 1/2 squared is what? 0.25, is that right? 3 times 0.25 minus 2. So we get what? Minus 1.25? Right. Minus 1.25. All right. Now, of course, what is that telling us about our curve? And what is that telling us about our surface? Now, well, you have a negative derivative, right? So what about this? What do you know about this curve at that point? Oh, there it is. Okay. So what do you know about this curve at this point where x is minus 0.5? I think this is minus 0.5 on the x-axis, right? So, yeah, that's right. It's downward sloping. Now, what does it mean to say it's downward sloping? Well, you're saying as x is increasing, right? The curve is going down. As x is in x value is larger, curve is going down. It's going down at a rate of minus 1.25, minus 1.25 units down every time x increases by. Determine that derivative slope. Right? So this curve is down. But now that also tells you something about the surface because the curve lives on the surface, right? So you also know the surface is doing what? It's also sloping downward. In what direction, though? See, that's the key, right? Okay, it's sloping downward in what direction? Because it ain't sloping downward in this direction. Okay? In this direction, I think it's going up, but in this direction, yes. Okay. How do we describe it? Awesome. In the direction of x-axis. So in the direction of the x-axis, okay, kind of some sense parallel to the x-axis, right? Okay, right in the direction of the x-axis, this surface is falling. I don't think that's true in the direction of the y-axis, so right? Okay. Parallel to the y-axis, I think the surface is in fact going up, right? Okay, so but we know something about the surface. And at that point, remember, this only applies, remember, this is calculus, right? So what we're saying only applies to this particular point, right? But at this particular point, in the direction of the x-axis, surface is, okay? And even know what rate it's falling at, right? Maybe that's the next question. Probably is. Oh, no. Okay. Just a repeat of this question. All right, so y'all try this one. Find the equation for the curve when x is equal to 0. So here we're going to set x equal to a constant. So that will give us a curve with y and z, right? So set x equal to 0. And you don't have to graph the curve, but just what's the equation? And what's the slope of that curve when y is equal to... What's the slope of that curve when y is equal to minus 1? Okay, you want me to show you the formula again. Where's that formula? Yeah, here's the form. There's the formula. So what curve do you get when you set x to 0? It's really easy, right? Okay, and x to 0. Yeah. And what's the slope of that curve at y equal minus 1? We're not setting y to a constant, right? So y can vary. So what's the slope of that curve from y? Just a minute, so work fast there. That's what this one. Curve. Slope. Okay, so let's see what we're going to get here. When x is 0, what is this formula reduced to? Is it just minus y squared? Because these two terms, if you plug in 0 for x, right, those two terms will disappear. So you get a nice easy curve. And right, so your curve there is z equal minus y squared. That's the equation for the curve. And now we want to find the slope of this curve when y is minus 1. So you just take the derivative, right, of that formula and evaluate it when y is equal to minus 1. So that derivative is minus 2y, right? dz dy is minus 2y. And so you'll have minus 2 times a minus 1, which is 2. Oh, for that curve, which is just quadratic now, so that curve should look like a parabola when we look at it. Remember, that's just going to be a trace on that surface, right? So we have a trace on that surface that looks like a parabola, and it's increasing at this rate when y is equal to minus 1. Let's see if that makes sense to us in the picture. So where is it? X is held at what? 0, right? So that there is the curve, right, when x is 0. So you're taking a plane, right? You're taking the plane x equals 0, which is parallel to the YZ plane. This is the YZ plane over here. So you're taking a plane parallel to the YZ plane and slicing it right through your surface at x equals 0. So that apparently is a parabola. That's the parabola minus y squared. And at y equal minus 1, which I think is right here, I think that's y equal minus 1. That parabola, is it increasing? Yeah, right. It's going up, right? Okay. At a rate of, that parabola is increasing at a rate of 2. So the surface is also increasing at a rate of 2, but in what direction? how would you describe the direction? Yeah, in the direction of the y-axis, right? Okay, in the direction of the y-axis, this direction, that surface is increasing at a rate of that surface is increasing at a rate 2. All right. Now you can see already kind of where vectors are going to play a role here, because we want to be able to calculate the rate of change in other directions, and to describe those other directions, which are pointing lots of different ways, right? Vectors will help us describe these other directions, right? Okay. So congratulations, you calculated your first partial derivative. That's what you did today. All right. You calculated a partial derivative. That's what you did. All right. So, well, we're just going to continue with this next time. So it's going to look a lot like calculus 1. We're going to compute a bunch of partial derivatives, and we have second partial derivatives as well. So we're going to calculate second partial derivatives too. Okay. And they tell us the same thing that second derivatives tell us in calculus 1. What do second derivatives help us with in calculus 1? Concavity, right? So it's going to help us with concavity here as well. All right. So, well, let's quit there. We're done. All right. So don't forget your homework that's due tonight, and I'll see you guys on Wednesday.